In this video, I will derive an implicit finite difference scheme for solution to the advection equation and show some results obtained using this scheme. This video follows directly from my previous video in which I derived the first order Upwind explicit scheme for the advection equation and assumes the results derived there. Consider the advection equation dc by dt plus u dc by dx equals 0, where c is the concentration of a dissolved substance and u is the flow velocity of the fluid in which the concentration is travelling, the flow celerity. As before, I'll assume that the celerity is constant and positive. We saw previously that the characteristics of this equation are a family of straight lines in the xt plane given by x equals ut plus a constant. We also saw that this tells us that, for the constant celerity case, the concentration distribution is translated in the x direction with speed u. This is the behaviour we hope to capture with our numerical scheme. The Upwind explicit scheme used a forward difference approximation to the time derivative and a backward difference approximation to the spatial derivative evaluated at time step j. For the implicit scheme, we will use both of these, but also use a backward difference approximation to the spatial derivative evaluated at time step j plus 1. We substitute our finite difference approximations in the numerical scheme as shown here, where theta is a parameter which lies between 0 and 1, i.e. we use a weighted average of the spatial difference approximations to estimate dc by dx. Note that if theta is 0, this is identical to the explicit scheme. The case theta equals 1 is what we would call a fully implicit scheme. Multiplying throughout by delta t and rearranging, we have this expression, where we're using the Greek letter rho for the non-dimensional Courant number. Note, we have rearranged this equation so that values of c at time step j plus 1 are on the left-hand side, and values at time step j are on the right-hand side. This scheme is known as the first-order implicit Upwind finite difference solution to the advection equation. Note that because there are two terms on the left-hand side of this equation, we have a system of equation which needs to be solved at time step j plus 1. This is why we describe the scheme as implicit. The most common such scheme is the Crank-Nicholson scheme, which has equal weighting across the time steps, i.e. theta equals a half. Now, if we write a equals minus rho theta and b equals 1 plus rho theta, then once we've chosen our numerical parameters, a and b will be constant. We know that the terms on the right-hand side are known when we reach time step j plus 1, so for convenience, I'm going to define a function phi which at point ij equals the right-hand side of the update equation, i.e. phi ij equals 1 plus rho theta minus 1 cij plus rho 1 minus theta ci minus 1j. Then our update equation can be written a ci minus 1j plus 1 plus b cij plus 1 equals phi ij. We've already noted that this generates a system of simultaneous equations at time step j plus 1. For most implicit schemes we would need a solver to deal with them, but in this case the nature of the scheme lends itself to a simple solution because of the upwinding. First, we rearrange the update equation so that only cij plus 1 is on the left-hand side. We have this expression. Now, provided we have an upstream boundary condition, we can use this equation to sweep across the domain in the positive x direction, starting our calculation at c0j plus 1. Let's have a look at how that works. Here we have our finite difference grid. We start from a set of initial values. These provide the values of phi for time step j equals 0 at each point on the x-axis. We then call our left-hand boundary value C01 and use our update equation to evaluate C11. This value is then used to calculate C21 and so on. Once we've swept across the whole grid, we can calculate phi at each point on the grid for time step j equals 1. Moving to time step 2, we call the next boundary value C02 and repeat the sweep. This formulation thus turns this particular implicit scheme into a pseudo-explicit one. Let's think about what is happening at a general point within the grid. We can see that our update equation uses the 4 points shown here, meaning that our domain of dependence is the rectangle lying between the 4 points. And here we see the alternative representation of that domain of dependence. Okay, so let's look at some numerical results. The results I'm going to show you are obtained using the Crank-Nicholson scheme, i.e. with theta equal to a half. Here we see the results obtained after half a second with a celerity of 1 and a current number of 1. We can see that the solution is diffusive, which is in contrast to the explicit scheme, which reproduced the exact solution for a current number of 1. This is typical of implicit schemes. In this second case, we have a much larger current number of 4. Here we can see that the solution is still diffusive and also exhibits a phase error. The wave in the numerical solution is travelling at a lower speed than that of the exact solution. However, unlike the explicit solution, there's no sign of instability. We don't see the oscillations and growth of the peak that the explicit solution exhibited for current numbers greater than 1. Thus, while we do have a loss of accuracy, this scheme has the advantage that we don't need to worry about the stability of the solution and can use much larger time steps. In this last example, we can see the results obtained when the current number is 10. The phase error has increased in this case, but interestingly the peak is not much different to that obtained with a current number of 4. In summary, we derived an implicit scheme for the advection equation, and we saw that in this special case where we have a first-order upwind approximation to the spatial derivative, we don't need to solve any equations simultaneously, and thus it's straightforward to implement and quick to run. Results obtained using an equal weighting across time steps, what we call a Crank-Nicholson scheme, showed that the scheme exhibits numerical diffusion but remains stable for large current numbers. It does, however, exhibit a phase shift which increases as the current number increases.